All right. Any other questions before we go on? So actually this diagram is messed up. I should have deleted it. Oh well. Can I delete it now, Ben? This diagram? How do I do? Hmm?
It's a picture, so you have to layer white. That's not all the camera.
All right, I'll delete it later.
Oh, I guess, okay. I couldn't see, it was two pictures on this one.
All right. So this problem, in figure 12 volts, L is 12 millihenry and R is 5 ohms. Determine the time constant of the circuit. The initial current through the resistor, the final current through the resistor, the current through the resistor, the voltage across the inductor. Okay. So we'll do the, and at t equal to 0 you close the switch. So okay, I'll draw a switch. Okay, so at t equal to 0 you close the switch. Determine the time constant of the circuit. The time constant of the circuit is L by R. Okay, so what happens is, you guys remember when you close the switch, the current in the circuit doesn't go instantaneously to its maximum value. It changes over time constant. It goes exponentially up, and the expression for the current as a function of time, you can check your notes, is given by e to the r. That would be the maximum current as if the inductor was not present. 1 minus e to the power of minus t by tau, where tau is the time constant and there's the time constant. Okay, so part 1 of the problem is asking you over what time, what is the time constant of the circuit, meaning what is the time scale over which things change. Okay, L is 20 millihenries and R is 5 ohms. Okay, 5 ohms. And so this is 4 milliseconds. Okay, so that's the time constant of the circuit. Things change over. Henries over ohms is seconds, and 20 by 5 is 4, and there's the milliseconds. Okay. Part B, the initial current through the resistor. So the initial current I0 is E over R 1 minus e to the power of 0 by tau, which is equal to 0. This is 1, 1 minus 1 is 0. Okay. C. Before I do that, I mean, if you guys recall from your notes, if you draw this thing, if you plot this, this is how current looks like as a function of time. At initial time the current is 0, and then it goes to its maximum value, E by R over several time constants. Okay. So in here all we did was find that, say, all we're saying is at initial time the current is 0. Okay. Let's see, what does Okay, so B is done. C, what does C say? The final current through the resistor. So final current is time at current at infinity, which is E over R 1 minus e to the power of minus t over tau. Okay, so we'll be a little more precise. T tending, oops. Okay, so this will equal E over R 1, okay, will equal E over R. Okay, so 12 volts divided by 5 ohms. So the steady state current will be 2.4 amps. Okay. And part D, the current through the resistor when T equal to 2 tau L. Okay, at T E by R is okay. And so this works out to okay, so at T equal to 2 time constants, the current is 2.08 amps. Okay, so let's go back to the graph. What we have found is the following. At T equal to 0, the current is 0. At 1 time constant, it'll be 65% of 2.4 amps. At 2 time constant, it's roughly about 90% of 2.4 amps. 2.4 amps is the maximum current. Okay, so that's what we're finding. All right. And what is the last part? The voltage across the inductor and the resistor when T equal to 2 time constants. Okay, so let me add a page. Okay, I'm going to draw that diagram again. Okay. You guys have to remember at all times, the sum of the voltages around this loop is 0. Okay, so what is happening is as the current is changing, the voltage across this guy is changing, so correspondingly the voltage across this guy is changing. Okay, because they all have to add up to 0. Okay, the current is increasing. Since the current is increasing, the induced EMF across this guy is in this direction. Okay. All right. So just keep that in mind. All right. So what is it that at two time constants is what we want to find? At two time constants, we just calculated the current. So IT, oops, I at two time constants is equal to E over R 1 minus e to the power of minus 2 time constants divided by that. And we just found this to be 2.08 amps. Did I did that right, correct?
Yeah.
Yeah. Okay. So now at two time constants, what is it that they're asking? The voltage across the inductor and the resistor. Okay. So across the resistor, voltage across the resistor is uh, minus IR. Okay, so if you're going clockwise, this it's minus, when we are saying minus, this point is at a higher voltage than that. The current is flowing in this direction. Okay, it's minus IR, and that is equal to minus 2.08 amps times R is, what is R? 5 ohms. Two point oh eight into minus 10.4 volts, and the voltage across the inductor is minus L di by dt. Okay, and so we have to find that, and let's do di by dt. So we're taking the derivative of this expression, with that being t. Okay, di by dt is so the derivative of the first term is 0. From the second term you get 1 over tau. So you guys can check this at home if you like. Okay. And tau is L over R. Okay, so all right, we'll need another sheet. Okay, so VL and di by dt is E over L. Okay, so we are calculating V of L at two time constants, so it's minus e to the power of minus 2 tau divided by tau equal to minus e over e squared. And that is equal to minus 12 volts divided by e squared, and that is equal to okay. And so let's make sure this makes sense. Like we said, this thing is working like that. This is a 12 volt thing, and the voltage, this is at t equal to 2 time constant. The voltage across this was 10.4 volts, and the voltage across this is 1.6 volts. This is high, this is low, this is high, this is low. 10.4 plus 1.6 is 12 volts. So you start off here plus 12 volts, you start off here, and we are going to go counterclockwise. So this is plus 12 minus 10.4 minus 1.6. Okay, so plus 12 minus 10.4 minus 1. Okay, as expected. Yep, Ben. This is squared. Oh, that's squared too in a parallel universe. Okay. Any other questions before we go on? We have 14 minutes.